Hi, welcome to Sunil Maths tutorial. Galois theory class number 2. Galois theory class number 2. In this video, let us learn some definitions and theorems. The very first definition, a root of a polynomial. Let capital E be the field containing another field capital F and f of x belongs to capital F of x be a polynomial. F of x belongs to capital F of x be a polynomial, and there is another field capital E containing capital F. An element alpha belongs to capital E will be called root or zero or solution. So remember that these words are same, root or zero or solution. These are same meaning in terms of root. So is called a solution of the polynomial f of x. Here it is the symbol f of x if it satisfies the condition f of alpha is equals to 0. So remember that capital F is a field containing in another field capital E, and there is a polynomial f of x that is defined over capital F of x. An element alpha belongs to capital E is called root for the polynomial f of x implies and implied by it satisfies the condition f of alpha is equals to 0. And then here an element a belongs to f is a 0 of the polynomial f of x if and only if x minus a, remember that. If small a is a root or alpha is a root, if alpha is a root of the polynomial f of x, then obviously x minus alpha is a factor. X minus alpha is a factor of f of x. So this is the definition of root, and a non-constant polynomial, a non-zero non-constant polynomial f of x of degree n have at most n zeros in the field capital F. So this is the definition of root, and remember that the terms 0, root, solution all are equivalent to one another. I think this is well known definition to everyone. Let us see the next theorem, and then we learn some definitions. Let us see the statement. Let f of x belongs to capital F of x be a polynomial of degree 2 or 3. Then f of x is reducible if and only if f of x has a root in capital F. So right, we prove this theorem. Let they given that f of x belongs to capital F of x be a polynomial of degree 2 or 3. This is important point. Degree of the polynomial f of x is either 2 or 3. Either 2 or 3. So we have to show that f of x, we have to prove that f of x is reducible. F of x is reducible implies and implied by f of x has a root in capital F. F of x has a root in capital F. To prove that, let us assume the first part. Suppose f of x is reducible. By the definition of reducibility, f of x can be written as product of two non-constant polynomials. By the definition of reducibility, f of x can be written as product of two non-constant polynomials. It means f of x is equals to f1 of x into f2 of x, where both f1 of x and f2 of x are non-constant polynomials, comma, each of degree less than 3. Each of degree less than 3, because the polynomial degree is given, polynomial f of x degree is 2 or 3. So right, remember that. Again, since degree of f of x is either 2 or 3, and this f of x can be written as f1 of x into f2 of x. What it means? degree of f1 of x and degree of f2 of x, either any one of them, either one of them is must be 1, must be 1. Among these two polynomials, f1 of x and f2 of x, the degree must be 1. One of the polynomial has degree 1. So let us take degree of f1 of x is equals to 1. If degree of f1 of x is equals to 1, then this polynomial f1 of x can be written as ax plus b, comma a not equals to 0. A not equals to 0. Now put x is equals to minus b by a. Then f1 of minus b by a is equals to a into minus b by a plus b. Simply you get minus b plus b, you get 0. It means f1 of minus b by a is equals to 0. It means x is equals to minus b by a is a root of f1 of x. If it is a root of f1 of x, obviously here f1 of x is a factor of f of x. This x is equals to minus b by a is a root for f of x, because f of minus b by a is equals to f1 of minus b by a into f2 of minus b by a. This f1 of minus b by a is 0, 0 into f2 of minus b by a. So obviously it is 0. So our point is right. X equals to minus b by a is a root for the polynomial f of x. So this is the required condition. Therefore we conclude that x equals to minus b by a belongs to capital F is a root for f of x. Is a root for the polynomial f of x. Hence, the polynomial f of x has a root in capital F. This is the first part. Next, we have to show that converse. Let us see the first part again. We assume that suppose I repeat the same, f of x is reducible. By the definition of reducibility, this f of x can be written as f1 of x into f2 of x, where both f1 of x and f2 of x are two non-constant polynomials whose degree is less than 3. Since f of x has degree 2 or 3, then either f1 of x or f2 of x must be of degree 1. Let f1 of x degree is 1, then f1 of x is equals to ax plus b. Put x equal to minus b by a. Obviously, f1 of minus b by a is 0. Therefore, x equal to minus b by a is a root of f1 of x. Therefore, x equals to minus b by a is a root of f of x. Hence, f of x has a root in capital F. Now, when we prove that if f of x is reducible, then f of x has a root in capital F. Right. Now, we are going to prove the converse part. In the converse part, we assume that f of x is reducible. F of x has a root in capital F. Suppose we assume that f of x has a root in capital F. We have to show that it is reducible. F of x has a root means f of alpha is equals to 0 for some alpha belongs to capital F. If f of alpha is equals to 0, then x minus alpha becomes factor of f of x. If it is a factor of f of x, then obviously the polynomial f of x can be written as x minus alpha into some another polynomial g of x, or by using previous theorem. In the previous class we learned a theorem. If there is a root, let f of x belongs to capital F of x and f of alpha is equals to 0 for some alpha, then f of x is reducible. This is the previous theorem. So by using that previous theorem, f of x is reducible over capital F. This is also right. F of x can be written as factor into some another polynomial g of x. It means f of x can be written as product of two non-constant polynomials. Therefore, if f of x has a root, then f of x is reducible. That's it. One of the important theorem for 5 mark section. Keep learning. So next we will learn one very important definition, primitive polynomial. Primitive polynomial. A polynomial f of x belongs to z of x is called primitive polynomial if the greatest common divisors of the coefficients of f of x is 1. So primitive polynomial. Primitive polynomial. A polynomial f of x belongs to z of x is said to be primitive polynomial if the GCD of coefficients of f of x is equals to 1. GCD, greatest common divisor of the coefficients of the polynomial f of x is 1. To understand this definition, let us see the examples. Suppose 2x square plus 3x plus 1 is a quadratic polynomial. What are the coefficients here? 2, 3, 1. Their GCD is equals to 1. They have only one GCD, greatest common divisor 1. Therefore, it is a primitive polynomial. Now see, 2x square plus 4x cube plus 8x plus 16 is equals to 0. Now the GCD of coefficients 2, 4, 8, 16 is equals to 2. Greatest common divisor is 2. Therefore, it is not a primitive polynomial. Not a primitive polynomial. So remember that a polynomial f of x belongs to g of x is called a primitive polynomial if the greatest common divisor of f of x is 1. Here are some examples. 5x cube plus 2x square plus 1. So here also the GCD of 5, 2, 1 is 1. So it is primitive polynomial. The next example is x power 4 plus 3x cube plus 2x square plus 5. It is also a primitive polynomial. So next let us see the definition of monic polynomial, one of the very important definition. A polynomial a0 plus a1x plus a2x square plus and so on plus an x power n over a ring capital R is called monic polynomial if an is equals to 0. Here an means leading coefficient. The same definition in another way we can say that any polynomial is said to be monic polynomial if the leading coefficient is equivalent to 1. So any polynomial is said to be monic polynomial if its leading coefficient is 1. Here you observe both the examples of polynomials. These two are primitive polynomials. X power 4 plus 3x cube plus 2x square plus 5, x cube plus 2x square plus 3, both are monic polynomials. And we learn two definitions, monic and primitive. Every monic polynomial is primitive. But primitive polynomial need not be monic. Remember that. Next definition, content of the polynomial. Suppose it is possible to write a polynomial f of x is equals to c into f1 of x. Where this c is equals to GCD of coefficients of f of x. Then where, and also remember that, and also here this f1 of x is a primitive polynomial. Then this factor c is called the content of the polynomial f of x. It is denoted by c of f. So important definition, remember, I repeat that. Suppose if a polynomial f of x can be written like this, c into f1 of x, where c is equals to GCD of coefficients of the polynomial f of x, and f1 of x is primitive polynomial. Then we say that this constant c is called content of the polynomial. polynomial f of x, and it is simply denoted by c of f. Instead of c, if you write here d, then it is very simple. C of f is equals to d. C of f is equals to d. That's it. So we understand this one by using this example. Here 2x square, here 2x square plus 4x cube plus 8x plus 6 is equals to 0 is a polynomial equation. Is a polynomial equation. Or simply it is a, now let us remove that equal to 0. It is a polynomial of degree 3. So the GCD is 2 here. The GCD is 2. So after making common 2 like this, you get x square plus 2x cube plus 8x plus 1. This is clearly a primitive polynomial. This is clearly a primitive polynomial. So this 2 is called content of this polynomial. Content of that polynomial. That's it. So remember that. So next definition. No, next there is a theorem. We prove that. So let us see the statement of the theorem. The product of two primitive polynomials is also primitive. One of the simple and easiest theorem. Let us see. The product of two primitive polynomials is also primitive polynomial. The same statement can be written like this also. If f of x comma g of x belongs to R of x, then content of fz is equals to content of f into content of z. So to prove this, we define like this. C is equals to content of f and d is equals to content of z. So remember that C is equals to content of f. It means C is equals to GCD of coefficients of f of x. And the next one, D is equals to content of G. It means GCD of coefficients of g of x. Now we have, so by the definition of content, that f of x can be written, by the definition of content, that f of x can be written as c into f1 of x, and g of x can be written as d into g of x, where remember that both you write g1 of x for our convenience. You write g1 of x. For our convenience, you write g1 of x. Here both f1 and g1 are primitive polynomials. Now multiply f of x into g of x. F of x into g of x is equals to c into f1 of x, d into g1 of x. So this is nothing but cd f1 of x into g1 of x. Now we have to prove that this f1 of x into g1 of x is primitive. Our aim is to show that f1 g1 is primitive. f1 into g1 is primitive. Now to prove this, let us define a prime number. Let us define a number. Let P be an irreducible element. P be an irreducible element that divides. P be an irreducible element that divides all the coefficients of f of x, f1 of x into g1 of x. Here it is. That divides all the coefficients of f1 of x into g1 of x. We are defining a number. One second. We are defining a number. P be an irreducible element that divides all the coefficients of f of x, f1 of x into g1 of x. Now that f1 of x can be written like this. f1 of x is equals to summation over I ai x power I, and similarly g1 of x is equals to summation over j bj x power j, where ai comma bj r belongs to the ring capital R. Suppose let us take as and bt be the first coefficients. As bt be the first coefficients of f1 g1 that are not divisible by p. Now the coefficient of x power s plus t, this is the important point. The coefficient of x power s plus t In the product, f1 into g1 must be in this form, plus and so on, as minus 1 bt plus 1 plus as bt plus as plus 1 bt minus 1. Because of we define f1 and g1 here, a summation over ai power x power I, summation over bj power x power j. So as and bt, the coefficient of x power s plus t in f1 g1 must be in this form, as minus 1 bt plus 1 plus as bt plus as plus 1 bt minus 1 and so on. And we define that p does not divides as, p does not divides bt. Therefore, p does not divides as bt. But already we said that p divides all the coefficients of f1 g1. This means except as bt. This is a contradiction because already we defined that p is the irreducible element that divides all the coefficients of f1 of x into g1 of x. But we get here a contradiction point because of r is a UFD. Polynomial ring capital R is a UFD. So f1 g1 must be primitive. f1 g1 must be primitive. Therefore, the product of these two primitive polynomials is again a primitive polynomial. Because of this condition, if f1 of x into f2 of x, if here let p be an irreducible element that divides all the coefficients of the product f1 of x into g1 of x, means here we are assuming that that product f1 into g1 is not primitive. Then only it is possible it divides all the one, because of capital R is a UFD. So anyway, you remember this property, the product of two primitive polynomials, is also a primitive polynomial. In another way, if f of x into g of x if f of x and g of x are two non-constant polynomials in the polynomial ring, then content of fg, product fg, is equals to content of f into content of g. So that's it. Keep in the next video we'll learn Gauss lemma and some another definitions. Keep learning. Wish you all the best.